Most things I've done in the last 10 years or so, with Shamit, they have all been directly sort of used Ribet's method. And then I think a lot of it has been influenced maybe somewhat indirectly by Mazur's paper. So it's a great honor to sort of come and speak here in celebration of these two great works. So I changed the title, and so what I'm going to do is I'm going to first present this strong form of Brumer's stark conjecture, and then tell you how it implies ET and C. So whatever I'm going to talk about is kind of completely disjoint from the theme of the conference, unfortunately. But I've given many talks about how to use Ribet's method for Brumer Stark, and so this is something I've talked less about. So maybe I'll do that's I thought I'll do this. Okay. So here's the setup. F is a totally real number field. And K is a finite abelian CM extension of F with Galois group G, or sometimes I'll write it as GK. And yeah, because afterwards I'll change this, I'll vary this field K, so I'll write it as GK when I'm varying the field. And as usual, S is a finite set of places of F. And I'll take this to be the minimal possible one. So all the Archimedean places of F and all the places of F that ramify in K, I think the notation is self-explanatory here. And T is a finite set of finite places of F, finite set of finite places of F disjoint from S. So S intersection T is empty, and then there is this Deligne-Ribet condition on T that T contains places of two distinct residue characteristic, or T contains two places of distinct residue characteristic. You can even assume that it has one place of large enough residue characteristic, large enough meaning bigger than degree of F over Q plus 1. And yeah, okay, so I won't write that down. So I'm not going to talk about the construction of this so-called Ritter-Weiss module, but I'll just tell you maybe some properties of it as we go along. So given this setup, there is a Ritter-Weiss module that we construct. And I'll denote it by nabla TSK. Right. So one thing that it sort of, one properties it has is it sits in this short exact sequence. So it's, yeah, it's a module over, yeah, I was going to write it later, but okay, it's a module over ZG. It's a G module. And yeah, so it sits in this XKS. So these are the usual things, but let me write them down. So CLT SK, this is CLT of K modulo the primes in S. So you kill all the places that are in S, and so meaning finite places. And CLTK, this is Ray class group of conductor, or so sort of primes above T. So this is product V. So W is a place of K which is above T of this conductor. And XKS, this is kernel of the degree 0 elements in. So SK simply means places of K above places in S, Z, and this is the degree 0 map. So it's just the kernel of this, right? So sorry, degree 0 elements in this. This is the degree map. So this captures this sort of, in some sense, units and then the class group. And oh, this is heavy. Okay. And yeah. Yeah. SK is the places of K above S. Yeah, S is downstairs and this is upstairs, right? Okay, so that's kind of the algebraic side, and let me tell you about the Stickelberger element that I want to work with. So LST chi S, this is product over all places in T, 1 minus chi of P, norm of P to the S minus 1 minus S. Okay, I've changed notation here. So, and then all places which are not in S, 1 minus chi of P, norm of P to the minus S inverse. So this is the S depleted L function, right? So Euler factors at S removed, and then you smooth it at this in some way, right? So, and then theta ST of K over F, this is an element in the, so because of the condition that I have in T, this will be an element in ZG. This is the Deligne-Ribet-Cassanugas theorem. And I'll tell you what this is. Such that for any character chi of G, when I evaluate this at chi, I get LST chi inverse 0. That's my Stickelberger element. And the last piece of notation I want before I state the refinement of Brumer-Stark is the following. So, so C in G or GK is the complex conjugation. And if M is a G module, then I denote M minus to be M modulo 1 plus Cm. Right? So that's the minus part as a quotient. And that's why it goes in the downstairs. So here's the conjecture that was made by, the following was conjectured by Burns, Kurihara, and Sano. And so we proved it first away from P equal to 2, and then also at P equal to 2. And this is the thing that uses Ribet's method. So it says that the fitting ideal of this, the minus part of the Ritter-Weiss module, so we can't say anything about the plus part, that's kind of much deeper, I suppose, is generated So this is fitting ideal as Zg minus module is generated by theta St k over f. Okay? So it's kind of a remarkable conjecture because fitting ideals are, I mean, especially over these kind of rings, are hardly ever principal, but this is the right object for which the fitting ideal is principal, and then it's generated by this. It's kind of this, having a principal fitting ideal is crucial for Ribet's method. Otherwise, I don't think we can get it off the, we can even get started. Okay, but as I said, I'm not going to talk about the proof of this theorem, which would probably have been more appropriate for this conference, but I'll talk about how to deduce the specific case of equivariant Tamagawa number conjecture from this. Okay, so as remarkable as this sort of statement is, there's some, maybe it's unsatisfactory in a particular way. So which I'll say, and then that's what I mean. At least for me, that's what ETNC tries to rectify, and so and I'll tell you what the formulation is that we use. Okay. All right. So the fitting ideals, they behave well, sort of under projection. So if chi is an odd character, so let's say this is in some finite extension of QP, and I can only talk about odd characters because I'm taking minus part, then what I have is then the theorem would give you sort of fitting ideal over O of this nabla TSK minus tensored over O, I mean this tensor is over ZPG minus. This thing is the specialization of this, and the specialization of this we know is chi inverse of LST chi inverse of 0. So it's sort of some sort of refined class number formula, but when there are these exceptional zeros or trivial zeros, you kind of get 0 equal to 0. And so it's in that particular sense, at least, the statement of this theorem is not very satisfactory, and that's what ETNC tries to kind of rectify. So let me write that down precisely, what I'm saying. Sorry? O is some finite, I mean, it's some finite extension of ZP. Yeah. Yeah, where chi takes values, right? Or some, yeah, you could even take it to be, yeah, fine. I mean, you could take it to be a number ring as well, that's fine. Okay, so, so if there exists V in S such that chi of V is 1, then sort of from the, because you're removing Euler factors at S, then it's kind of well known that this thing would be 0, and on the other side, this fitting ideal is also 0. You can see that X tensored with O turns out to be an infinite group, and so this is fitting ideals of infinite O modules is 0. So you get, so basically you get sort of 0 equal to 0, and so it's probably not that interesting, right? So ideally, sort of in this sort of situation, we should be working with, we should be working with the smallest possible S for that particular chi, S minus V, and maybe, throughout all the primes that are that split completely in the extension cut out by chi. Right. And so this is what ETNC tries to do. But that theorem would also try to do that if you just take a smaller extension. But we want to do it sort of equivariantly for k over f directly, right? Okay, so how does one do it? So there are sort of very general formulations of equivariant Tamagawa number conjectures. Very much like one of the conjectures that appeared in Merrell's talk this morning about particular generators in the determinant line. But I won't give that formulation. The formulation that I'm going to present here is due to Kurihara. And for that, I need to kind of tell you one more thing about the Ritter-Weiss module. So the construction of Ritter-Weiss module, it gives you some sort of what is called a quadratic presentation of the module, which tells you even before proving that theorem that, yeah, so by the way, one thing I should have said is, one knows a priori before proving this theorem that this fitting ideal is principal, okay, and that's crucial in the proof, and it comes from the construction of this Ritter-Weiss module that the fitting ideal is principal. So it's not the method that we have won't work by sort of an arbitrary. If we don't know that the fitting ideal of this module is principal, we can't. The method won't work, and it sort of doesn't come out of the theorem that it's principal. Okay, so the construction of So what we need to do for the construction, and I won't say anything about the construction, but just tell you that it has a quadratic presentation, by which I mean the following. So what I have to do is I have to fix a large enough set S prime of places of F, so again the downstairs field, such that, well, S is contained in S prime, and I won't say what large enough means. One of the things is that the class group in which you kill all the places in S prime, that becomes trivial. That's one of the conditions, but you need more about decomposition subgroups at S prime. I won't say anything, but it's a large enough finite set. Finite set. And then S prime is still disjoint from T. Okay, then the construction of gives a presentation as ZG modules. So we have specific modules that one uses, and so this one depends. So this nabla doesn't depend on the choice of S prime, but the presentation does. And I'll say a word about this, the nature of this presentation. So the B module is kind of very simple. It's a free ZG module of rank, the number of elements in S prime minus 1. A priori, we only know that this thing, okay, yeah, so is a projective ZG module of constant rank I'll just say rank number of elements in S prime minus 1. And here is a conjecture of Kurihara, which says that this is VTS prime K is a free ZG module, and so the rank would be this, right? Okay. Yeah, maybe I'll also give this a name, FK. All right. Huh? Which, the V's or the B? I don't know. Okay, yeah, I think what I'm going to say next is probably what you're alluding to. So, yeah. So again, the construction of this, we proved that, so again from construction, these things behave well when you take co-invariance. So if you take a subfield such that this is Cm again, then you have the corresponding modules over E, and what you have is Vt S prime K. If I take the co-invariance under K over E, then I get Vt S prime over E. So it's the same set S prime, by the way. And so this will be a Galois group of E over F module of rank number of elements in S prime minus 1. So it's the same rank over the smaller group. And the same thing holds for B. Huh? No, not for the boundary map. Yeah, that's important, I think. But, for the map F. The map F, no, it need not be injective. No. Was that what you had asked? Okay, thanks. Okay. So, so because the rank doesn't go down when you take the covariance rank over the smaller group, as a module over the smaller group, they'll, if you believe the conjecture, then they'll still be free of the same rank as the 1 over K. If you fix a basis for over K, then you'd get an induced basis for over E. Okay. All right. So again, the following the following was conjectured by Kurihara, and he proved that this is equivalent to ETNC. So this is the minor ETNC for the minus part of the trivial motif, I guess, and this extension K over F. So here's the theorem. So this was proven by Bullock, Burns, Dowd, and Seo. I mean, they have a elaborate machinery of this scarcity of Euler system. So they also prove some conjecture of Coleman about rank of Euler systems in some general setting. And as a consequence of their machinery, they get this theorem. the main input is the previous theorem that I had, this conjecture of Burns, Kurihara, and Sano. And then we do the, we have it's basically inspired by them, but maybe a simplified version of their proof. So, okay, so the first thing, it's not the first thing we prove. We kind of do it prime by prime, and as a result, we get, I'll write it not in a way that we prove it, but here's the thing. So we prove that the minus part is a free ZGK minus module of rank S prime minus 1. So we can only prove the conjecture of Kurihara on the minus part. And then, the thing about BS that's known that is free module. So there's nothing to prove there. So we fix so once you fix a basis, for VK and BK, you get induced basis for VE and BS prime of E, because the rank doesn't go down, right? As ZGE minus modules, right? Free modules over this thing. Right? So if the rank were to go down, then you can't say that you get a basis. Okay. But the rank doesn't go down. And so you can, with respect to this choice of basis, you can talk about determinant of this connecting map. And the second part of the theorem, which was again Kurihara's formulation of the ETNC, is the following. Then there exists maybe okay, you get a basis, so that's fine as a sentence. There exists a unit YK in ZGK minus, right? So unit such that determinant FE, so the minus part of that map is equal to, you take the reduction. So I'll tell you what this map is, but you can imagine what this is. So theta SE T E over F. Right? So SE is the so I only wrote S, right? So SE is S infinity F union only the places that ramify in E over F. Right? So the previous thing was S. So S was SK. So S is SK in the notation that I had before. T is the same T, that doesn't change. And then this reduction is the map from ZGK to ZGE. Right? So the natural projection map from GK to GE. So from the theorem that I had before, the ideal generated by this is the fitting ideal of Nabla. And so the theorem would say that the ideal generated by this is same as the ideal generated by this. So they do indeed differ by a unit. One has to be careful about sort of things where you have zero devices. But anyway, they differ by a unit. This theorem is saying that unit comes from K. Right? So that's kind of the the non-trivial part, that you can choose once you, so yeah, this determinant depends on the choice of basis upstairs. Once you have that choice and you choose the basis consistently for K and E, this unit also comes from K. Okay. Yeah. Yeah.
So this is equivalent to ET and C for what?
So the trivial motive over, so I guess the notation would be H0K and Galois group of K over F, and the minus part of that. Yeah. 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 Yes. Yeah, GK was Galois group of K over F, remember? Right? Yeah, yeah, yeah. No, it's not the absolute Galois group, which is like the usual notation, but no, this is, yeah. Yeah, because I'm varying my K now, so. Okay, so maybe in the remaining half of my talk, I'll say how this is deduced. So this is in some sense an Euler systems argument. So as I said, completely disjoint from the theme of this this conference. But the other thing I want to say is kind of, I never, yeah, before this work of Bullock, Burns, Dowd, and Seo, I did not imagine that this could be obtained from the theorem that we had proved, right? Because that's an equality of ideals, and then we want something like this. Yeah, so it's not, as you will see, it's not very hard, but it's kind of, was sort of difficult for me to imagine that it could be proven from what we had done before. Okay, so step 1 or step 0 is you can, you can do p-adic stuff. So, yeah.
So before you started talking about ET&C, you said, you gave this example about a trivial 0 equals 0 formula. Can you say how does this theorem resolve that 0 equals 0 formula? Or?
Yeah, because, it's, it doesn't, I mean, not in some direct way, but you see this thing is like the yk is the difference between the two sides at k, and the same unit yk is also capturing the difference between this and this. So as I said, if I'm working with chi, if I want to specialize things at chi, then rather than working with k over f, I should be working with something like k, this thing, right? This kind of stuff. And so that's my E. And so I should be working with this, and so I should be specializing this rather than the theta upstairs. And so in that sort of way, it kept, in some indirect way, it's.
Get rid of the YK.
Yeah.
Now we're saying we can choose a basis upstairs that at least have the equality of the determinant with theta, but not just for K, but for all the subfields at the same time, including like if you pass to the fixed field of chi,
Yeah.
then you're getting rid of the 0. So it's a way of making a statement that works for all characters, including ones with trivial zeros. That's like a Brumer statement, but isn't just a fitting ideal of one model.
Yeah. So to repeat, because you don't have a microphone, I'll just say that. So what Shamit said is that, yeah, one way to sort of formulate this is you choose a basis upstairs so that fitting ideal of fk minus is equal to theta sk comma t of k over f, and then the induced basis at all level will give you this equality without without this unit. So it's an equality of elements on the nose. So you are getting this equality at all the intermediate fields, on the nose between two elements, including this field. So, okay. So, so this I won't say much about this. So enough to prove this kind of statement after tensoring with ZP for every prime P. So this I suppose you can believe that this kind of thing would hold. Right? It requires some study of like projective modules over ZPG are much easier than projective modules over ZG. So you need some work to show that from this over ZP for every P, you can pass to ZG, but yeah, it can be done. So once you do that, you have to kind of change your, so although I stated these two theorems in this way, they kind of, you have to prove them prime by prime, and when you do it prime by prime, you have to change your set S and T in a specific way for various modular constructions to work. And once you have those with modified S and T, then you can go back and prove things. So it's kind of a very roundabout argument. So here's how you change your, so altering the set. Yeah, so this, maybe I could have just ignored all this and told you about the algebra, but yeah, this is required for the modular constructions that go into the proof of the first theorem. So instead of S, you change your, I'll write sigma. So you change your S, you throw away some places. So V in S ramified K over F, you only keep primes that are above P, and then you change your T by throwing all the other ramified places in T that I'll denote by sigma prime. So this is so I take all the ramified places that are not above P, and I put them in my T, and I call that sigma prime. So the first theorem that I stated with equality of fitting ideal, that the fitting ideal is generated by something, that's we first prove it with this set. So let me kind of just say that here. So what we in fact prove is the following theorem first. This is that the fitting ideal over ZP GK minus of nabla sigma prime K sigma K of K minus, and then you base change to ZP. This is generated by theta sigma K sigma prime K of K over F. So I have just changed my set S and T to sigma and sigma prime. And these are not the kind of thing that are that's usually considered. So yeah, I mean, but this also turns out to be integral. It lives in ZPG. Okay. So again, it follows from Delin-Ribet Kassav-Nogues theorem. Okay. All right. So if I want to deduce this ETNC from something like this, so what goes wrong? Right? So it's easy to figure out what goes wrong. Let me. So I have chosen basis of V and B over K, and then I take the induced basis over E. And so this theorem gives, so step 2, YE. So for some unit, and now my T is also changing, right? So I have to be careful, but I am going to at times I think ignore these issues with changing T and changing, yeah, I mean changing S I have to be careful about, of course, but okay, let's see how this goes. So for some YE in ZPGE minus units in here, right? Okay, so I should be working on the component of ZPGE where my theta is non-zero divisor. So let me. Okay, maybe let me ignore that for a minute and write down what I want to write down. Okay, so I have my F, and then I have my E, and I have my E prime and K. So both E and E prime are CM fields. Then what I have is, if I take the restriction from E prime to E of theta sigma E prime, sigma prime E prime, sorry about this notation, this becomes P E prime over E of theta okay, sigma E prime, sorry, sigma E, sigma prime E prime of E, yeah, I think I've been writing it like this, right? So what is this P? E prime over E. These are the Euler factors, that the extra Euler factors that you remove here, but not here. This is sigma of E. So this is all V in sigma of E prime minus sigma of E. This could be empty, but if it's not, then it's 1 minus sigma V inverse. So this is the Frobenius at V. Inside, so this is ZP GE, right? Or minus if you like. And on the other hand, of course, since the way you have chosen your basis, if you take determinant of Fe prime minus part, I mean everywhere it's minus, this is equal to determinant of Fe minus. So this is fine. And so if you compare it with that, the consequence of that theorem, what you get is the following. So what you get is, if you reduce this, E y E prime minus y E P E prime over E, and then theta of, what should I have, sigma E sigma prime E prime, so I have to keep this, but I mean changing this thing to sigma prime E, it just changes things by a non-zero divisor, so it's going to be okay. So this is 0 in ZPGE minus. So what I have to do is I have to sort of take the, I have to take projection onto the components of this where this is non-zero divisor, but I'll ignore that, it just makes no, so I have to multiply this by a particular idempotent, which one can do, but I'll ignore that subtlety for now. I mean, although I agree that sort of zero divisors are the main things here, but I'll ignore that and sort of proceed by saying that, and put it in quotes, that this gives that P E prime over E is 0, okay? And now if this were non-zero divisor, then I would get that this is equal to this, which is kind of what the what ETNC requires us to do. But this is always a zero divisor, right? So P E prime over E, this is product over V in sigma E prime minus sigma E of 1 minus sigma V inverse, right? So this is a zero divisor, always. So that's kind of not very useful. So how do we cancel this? That's kind of the problem. And so this is why I never thought that we would be able to do this from the theorem that we have. But what happens is by going to bigger and bigger extension, doing some sort of horizontal argument, you can actually cancel that out, right? So that's what I'll explain next. Okay, and as I said, one has to be careful here about two things, which I won't be. One is sort of what, this is zero divisors on some components, so I'm not going to be careful about that. And then this has changed. I should have sigma prime E here, but again, that changes things by a non-zero divisor, so I'll be less careful about that. Okay. Okay, so, I don't have anything written. So step 3 is the following. So I'm going to make a definition first. A family like this will be called a norm-compatible family. Okay, so this is kind of the definition inspired by Euler systems, I guess. So E inside K, this is a CM field. So this is in product E inside K, ZP GE minus is called norm compatible if it satisfies something like this. So maybe I'll denote this by Z. If reduction from E prime to E of Z E prime minus Z E P E prime to E is 0 in Z G E, Z P G E minus. Yeah. Okay? So, and then if I have a, yeah, okay, so I'm not doing much in, okay, what am I doing in step 3? Okay. All right. Okay, so in step 3, again, I won't tell you what how to do this, but it's kind of, so what I'm going to do is I'm going to take a bigger extension. So let K prime over F be a finite abelian CM extension such that, so two things, one is K is contained in K prime, and the other thing is this set sigma for K and K prime, they are the same, okay? So these were infinite places of F and all the places above P that ramify in K. And all I'm saying is that the places of F above P that ramify in K is same as the places of F above P that ramify in K prime. So if there is such an extension, then I can extend my norm-compatible system from K to a norm-compatible system over F, over K prime. Okay? What does that mean? Let me write it down here. So then, given a norm-compatible system Z E inside K, we have a norm-compatible system Z tilde E inside K prime such that Z tilde E is equal to Z E for all E inside of K. Okay, so I get a bigger norm-compatible system attached to this K prime. That's what it means. So, so once you know that you can extend it to certain bigger fields K prime, you just have to choose this K prime carefully so that you can cancel out the Euler factors. So how do we do that? That's kind of the final step, I guess. Yeah. So step 4, this is a good choice of K prime. So what do we do is we, yeah, so this is some modified version of, this is some Grunwald-Wang theorem from the Neukirch-Schmidt-Winberg book that I learned. So you want to choose a K prime which satisfies, so locally it has to satisfy certain conditions, right? So sigma of K is sigma of K prime, that of course we need there. And then oh yeah, so I want to cancel this Euler factor when I go from K to E, right? And so I take V dividing P such that V is not in sigma K. If all primes dividing P are in this, then there's nothing to cancel. This Euler factor that we are multiplying by is just 1, and we are not doing anything. So I fix such a thing just to explain this idea. Otherwise I have to fix all of these things, but yeah, let me fix one and sort of tell you what the idea is. Why are we, yeah, sorry, oh yeah, you're asking this one, right? Why are we able to, it's kind of, yeah, I've forgotten what the proof is. It's, let's see. So this is kind of what is called scarcity of Euler systems. So it's some computation you do, like in these infinite systems, like Euler systems are of rank 1. So yeah, I don't know how to explain it in a couple of lines actually. So anyway. Sorry? Huh? Sorry, I couldn't hear.
We're not going to just say ask what Samir said, that you do the whole story again with K.
Yeah, yeah.
You get back what you had for K.
Right, but there's some I mean, yeah. So basically, you go back to K, and then you sort of see that things differ by a unit over K, and then you can lift this to a unit in K prime, and then change everything by that K prime, that lift of arbitrary lift of that unit, and you get this. But yeah, so it's right. Well, I mean, I don't know if that's kind of helpful to say. Yeah, where was I? Okay. Then the decomposition subgroup has the same size over K or K prime for all W's in sigma K, which is same as sigma of K prime. Right. And then at this particular V, if I take the sigma, I'll denote it by the same symbol sigma V, whether I'm taking it in sigma in GK prime or GK. Those will be two different elements. But in this bigger thing, this has order divisible by. Oh yeah. So I should fix some large. Yeah. So fix some large integer m. So this is divisible by p to the m. Okay. So I can make this choice of K prime. And yeah, so what I have then, roughly, yeah, so just to tell you what the idea is. So what I have now is something like okay. Sorry. So I should have done this for E and E prime, but okay, let me try this. So what was my aim? So I have something like this. So this is inside GE, and this is 0, and I want to cancel this, right? So what I'm going to do is I'm going to choose. I'm going to choose E prime for this E this way, and then I'm going to choose. I'm going to take my K prime to be K E prime, I think. Let's try that. So, maybe I should have used a different notation there. Okay, so choose E prime and K prime as above, with given by this Grunwald-Wang theorem. So then what I have is so reduction from K prime to E prime, Z K prime minus Z E prime, 1 minus sigma V inverse. This is 0. This is inside Z P G E prime, right? What this means is that this element this belongs to 1 plus sigma V up to sigma V some n prime, or I don't know, n prime minus 1, I guess. So this belongs to this ideal. And then I reduce everything to then apply Yes, so this n prime is the order of sigma v inside this, and then I apply reduction from e prime to e, so I would get reduction from k prime to e z k prime minus reduction from e prime to e of z e prime. This thing belongs to some n prime over n, 1 plus sigma v, and so on up to sigma v to the n minus 1. But this is now inside zp ge minus, right? So you get this factor here, and this n is sort of bounded because it just depends on e. And because of the choice of our sigma e and sigma e prime, this just becomes, yeah, I think I should have been. But this just becomes reduction from k to e of zk minus ze. And this belongs to, so this is some large power of p, so p minus some constant, p to the m minus some constant, right? And then as you can choose m to be arbitrarily large, and you'll get that this is equal to 0. So that's kind of roughly the idea how you cancel this thing. Okay, so I'll stop here.